DeepSeek just shipped a second version of its V4 model that isn't a new model at all. Same weights, same checkpoint, one bolted-on module, and it's 85% faster. Every LLM decode step is the same trade. One forward pass through the model produces exactly one token, then that token feeds back in for the next pass. The bottleneck isn't compute, it's moving the model's weights from memory to the chip, so most of a decode step is spent waiting on bandwidth, not doing math. DeepSeek v3 attacked that with multi-token prediction. Extra lightweight modules bolted onto the trunk, each one predicting the next token conditioned on the real hidden state, plus the token the previous module just guessed. At inference, those same modules draft several tokens in one pass, the main model verifies the whole draft at once, and rejection sampling throws out anything that doesn't match. The output is identical to token-by-token decoding, it's just faster. DSpark isn't a new DeepSeek model. Hugging Face's own model card for DeepSeek v4 Pro DSpark says it directly. Not a new model, the same checkpoint with an additional speculative decoding module attached. Same for the Flash variant. The method behind that module has its own paper, DSpark, Confidence Scheduled Speculative Decoding with Semi-Autoregressive Generation, and it's already running in DeepSeek's live production serving. It shipped June 27th, 2026, about 2 months after base v4 went live in April. Under the hood, both DSpark variants keep v4's own training recipe untouched. Muon Optimizer, over 32 trillion pre-training tokens, the same two-stage post-training. DSpark only changes the drafting and verification path bolted on top. The paper behind it lists Xin Cheng and co-authors as the team, and DeepSeek confirms DSpark is running under real user traffic right now, not just a benchmark exercise. DSpark's drafter is built on something called DFlash, and it works nothing like MTP's chain. Instead of predicting draft tokens one after another, DFlash produces all of them in a single forward pass. Hidden states H1 through H gamma, and their logits come out together. Drafting cost barely grows as the block gets longer, because you're not waiting on a chain of sequential passes. MTP is cheap and chained. DFlash's backbone is parallel and flat cost. That's the opposite trade-off. Draft tokens don't get more expensive as gamma grows, because the backbone reuses the same forward pass for all of them. That parallel speed comes at a cost. Acceptance rate collapses toward the end of the block, because each later position is marginalizing over every possible predecessor, instead of conditioning on the one token that actually got sampled. On code tasks, DFlash's acceptance drops from 0.87 down to 0.78 across the block. On chat tasks, it falls from 0.72 to 0.63. A sequential drafter like Eagle 3 stays flat or even improves across the same span. Purely parallel drafting has a decay problem baked in. It's the same failure mode any purely parallel guesser runs into once you stop conditioning on ground truth. DSpark's fix is a second, cheap pass stacked after that parallel backbone. It's a lightweight sequential module, either a low-rank Markov head that just looks at the immediately preceding token, or an RNN head that keeps a running state across the whole block. Either way, it injects the real, actually sampled previous token back into the picture, which is exactly what the parallel backbone was missing. That's what stops the decay from the last chart. The sequential piece stays cheap. Its compute is kept far below the parallel backbones. None of this touches the target model's own weights either, only the small drafting stack changes. On top of that, DSpark adds a small confidence head. It scores each draft position from 0 to 1, trained against how likely the target model actually is to accept it, then calibrated with a technique the paper calls sequential temperature scaling. That confidence score isn't arbitrary either. It's trained against the actual total variation distance between the draft and target distributions, the real mathematical measure of how likely a rejection is. By the way, I post one of these daily. Subscribe if this is your thing. A hardware-aware scheduler takes those confidence scores plus live GPU throughput and decides, per request, how many draft tokens are even worth sending for verification. Low-confidence tail tokens get cut before they cost a verification pass. Plain MTP always verifies a fixed number of tokens no matter what. DSpark doesn't. The sparsity here is about which tokens get checked, not about the model's weights. DSpark doesn't prune or shrink the trunk at all. Run head-to-head against Eagle 3 and plain DFlash on Qwen3 and Gemma 4 targets. DSpark wins clearly. On Qwen3-4b, Eagle 3 gets an accepted length of 2.39 on chat. DFlash gets 3.7. DSpark gets 3.64. On code, Eagle 3 gets 3.69. DFlash 4.40. DSpark 5.13. On math, Eagle 3 5.14. DFlash 5.40, DSpark 6.11. Averaged across 3 Qwen3 sizes, DSpark beats Eagle 3 by 30.9%, 26.7%, and 30.0%, and beats plain DFlash by 16.3% to 18.4%. Scale the target model up, and the pattern holds. Qwen3 to 8b lands at 6.17, 5.16, 3.72. Qwen3 to 14b hits 6.21, 5.26, 3.70. That's consistent across 3 different model sizes. DeepSeek's production servers confirm it. V4 Flash, 60 to 85% faster per user. V4 Pro, 57 to 78% faster. Both measured at matched throughput. Turning it on is one flag. You launch vLLM with a speculative config JSON that names the method DSpark, sets num speculative tokens, and picks a draft sample method. No custom draft model to train or download, because the module ships inside the DSpark checkpoint itself. The catch is what you're launching it against. This only works through vLLM or SGLang. There's no llama.cpp or GGUF path for DSpark today. That single flag is the whole integration. There's no separate draft model download or config file to keep in sync. Once the server's up, you hit it like any OpenAI compatible endpoint. Nothing about your client code changes. DSpark's speedup is entirely server-side. The only knob worth tuning is num speculative tokens. The paper found that scaling the draft block from 4 tokens to 16 adds just 0.2 to 1.3% to full round latency, but improves accepted length by up to 30%. Bigger blocks are close to free here, because the parallel backbone doesn't pay per token like a chained drafter would. None of that software is the barrier. vLLM and SGLang are open source. Plenty of you already run them locally. The barrier is what DSpark is bolted onto. DeepSeek's own recipe for Pro DSpark calls for 4 GGUF 300 nodes, straight data center hardware. Even the smaller flash tier needs something like 110 gig of combined memory for its smallest usable quant. And there's no GGUF version of DSpark to shrink that with CPU offload, the thing that normally lets a consumer GPU punch above its VRAM. The DSpark checkpoints also ship in a mixed FP4 for experts, FP8 for the rest format. The plain, non-DSpark base stays full FP8. That's smaller on disk, but it doesn't change the GB300 class memory math above. The software's free. The weights aren't. DSpark isn't free lunch everywhere. The paper says it's straight. For complex queries with inherently low acceptance rates, the upfront drafting compute is unrecoverable. That's real cost with no payoff on hard, unpredictable prompts. Accepted length is also uneven by domain. On Qwen3-4b, it's 5.57 on math, 5.12 on code, but only 3.49 on open-ended chat. A secondary source puts real-world results as wide as 51% to 400%, and warns that on out-of-distribution prompts, acceptance can collapse enough that DSpark ends up slower than plain decoding. If your workload is agent tool loops or code generation, this is a genuine win. If it's free-form conversation, expect less. My take: DSpark is the right shape of fix, adaptive instead of fixed, but it's a serving framework feature for people running data center scale DeepSeek deployments, not a weekend project for your home lab. That's DSpark. Same DeepSeek v4 weights, a parallel drafter patched with a cheap sequential fix, and a confidence scheduler deciding what's even worth verifying. It's a serving problem solved properly, just not one you can run on a single GPU yet. I cover stuff like this daily. Subscribe if you want the next one.